Is the first speaker of today, Marco Mazzucchelli from Lyon. And Marco will tell us about spectral characterizations of Besse and Zoll Reeb flows.
Thank you very much. I wish to thank all the organizers for inviting me to this amazing conference. My talk will be a summary of three related projects. The first one with Stefan Suhr, who is a postdoc in Bochum. The second with Christopher Gardiner, and the third with Victor Ginsberg and Bajak Gorel, who are also here. It's about a special class of, it's about Reeb flows, all of whose Reeb orbits are closed. But actually the story begins with geodesic flows. So let me begin by reminding the famous closed geodesics conjecture from Riemannian and Finsler geometry. So there are two conjectures. The first one, many people in the audience know it, is that every closed Riemannian manifold of dimension at least 2 has infinitely many closed geodesics. So most people are familiar with closed geodesics, but still, a closed geodesic for me is a geodesic that closes up in a periodic way after a certain time. So I will abbreviate closed geodesics with CG. And this conjecture is known in many cases, but it's still open in general, and notably it's open for spheres of high dimension. And the conjecture actually fails for Finsler geometry, in Finsler geometry. And there the conjecture is rather every closed Finsler manifold of dimension d, any dimension d now, has at least d closed geodesics. So both conjectures are known in certain cases, as I said, but they're widely open in general. And there hasn't been any real progress in these two specific questions since the 1990s, early 1990s. But there has been progress on a subconjecture, which I'm going to state because it's relevant for this talk. Subconjecture. And what is it? Yeah, maybe it's d or d plus 1. But d is okay, right?
Yeah, I think
if you can prove it for d, I'm happy enough.
I think it's probably true, but I'm not sure if it's the right lower bound.
Oh, sure, it could be, but yeah, one can even phrase harder conjectures, but these are already out of reach, so it's. So there hasn't been progress on these two conjectures, but there has been progress on a subconjecture, which says that every although it's still an open problem, every sphere, Sn, Riemannian or even Finsler, of dimension at least, well, let's say of dimension at least 5, has more than one closed geodesics, at least 2 closed geodesics. So finding one closed geodesic is very, very easy. Nowadays, since the work of Birkhoff and then Lustagnik, Fett. But finding the second is a big deal. And this generality is still open. So mention 3 and 4, there are published proof. Yes, for the Riemannian case. I think for the Riemannian case, let's say for the Riemannian case. The Riemannian case is hard enough. And by the way, it's very important here. When I say Finsler, I really mean general Finsler. Namely, Finsler means that on every tangent space you can measure the length of vectors. But general Finsler means that this equality is not verified. So the length of a vector may be different from the length of minus the vector. So today I'm going to discuss actually a conjecture that's slightly harder than this, and it's related to the topic of the title. So let me introduce Zoll manifolds. So our Riemannian manifold Mg is Zoll. So it must be closed. I don't write closed anymore. Is Zoll when its unit speed geodesics all have the same length. So have same length TL. And this is a remarkable class of Riemannian metrics, or Riemannian manifold. There has been a lot of research about them since the 1950s. And there's been a lot of progress until the 1980s. Then things quiet down a little bit. But now recently the subject sort of regained attention. Having a Zoll Riemannian metric is very special. Not every manifold admits a Zoll Riemannian metric. Essentially, the only known examples are spheres with a constant curvature metric and all the quotients by isometry. So all the so-called crosses, RPN, CPN, the quaternionic projective space, and also more exotic object, which is the Cayley plane. Have the same, for me, a geodesic, I give the wrong definition, sorry. When its unit speed geodesics are all closed and have the same length. So for me, a geodesic is just a one-dimensional submanifold, possibly immersed. Yeah, it's a one-dimensional submanifold, so it's a. No, but you're right. Yes, non-iterated once. The same period I wanted to say. Period. Sorry. Yes, if I talk about length, I don't need that. Sorry, but I'm being very sloppy. I didn't have coffee. And okay. So what about Zoll manifolds? Let me give a few more definitions. So usually Riemannian geometry, and by the way, this can be defined for Finsler manifolds as well, exactly in the same way. In Riemannian geometry, there's a well-known object, which is the length spectrum. In symplectic geometry, we call it the action spectrum. It's this is the period, it's the same, so let's say minimum period here. Sorry about this definition. So this is the set of periods of the unit speed closed geodesics. So now coming back to Leonardo's question. So now I'm considering all the periods. Namely, if you have a geodesic with unit speed that closes up after period 1, then 1 is inside here, but also all the multiple, all the integers. Okay? If you don't consider the integer, then you have a subset of the spectrum that gives somehow more information. It's what's called the prime spectrum, denoted with a little p. So this is a set of minimal periods of the unit speed closed geodesics. So namely, if you have a geodesic that closes up after period 1, 1 is inside here, but 2 is not necessarily inside here unless there's another geodesic that closes up precisely after period 2. Okay? And then if one works with surfaces, one could also consider another more restrictive spectrum, which is the simple spectrum. Well, you can always define it, but it makes sense only for surfaces, essentially. I write it with a little s in here. So it's sigma s mg is the set of periods let's say, periods of the unit speed simply closed geodesics. So minimal periods. So in other words, this could be a geodesic, this curve. It's not iterated. Let's say it closes after period 1. It's not iterated, but it's not simply closed because it has a self-intersection. Simply closed geodesic is really something that closes up without self-intersections. Sorry about that. Minimal periods of the unit speed simply closed geodesics. Okay, is it?
So you're not considering, also that's you're not seeing.
Right, so this. Not this, but this. Okay, is it the definition clear? Okay, so here's a conjecture that's much less known than this, but it implies a subconjecture. I stated for Riemannian, but well, it's Riemannian or Finsler actually. If the prime spectrum of a Riemannian manifold, or even a Finsler manifold, is a singleton, contains only one element, then the manifold is Zoll. So in particular, this implies that every closed manifold has at least 2 closed geodesics, because if you had only one, then the prime spectrum would be a singleton, but then every geodesic would be closed. So this implies a subconjecture there, so it's a difficult question. And in this business, as many people know, it's very easy to formulate conjectures because it's very hard to disprove conjectures. So usually the rule is that you're allowed to formulate a conjecture if you can prove it in one case. The rule of elegance, but not everybody respect that maybe. So indeed this conjecture is a theorem, and that's the first result of today. It's something that was claimed by Lusternik, but I wrote down a proof with Stefan Suhr, and so it's due to Suhr and myself. But it's based on the work of Lusternik and Schneermann in an essential way. So maybe I should add also Lusternik and Schneermann. I write just LS because everybody knows Lusternik and Schneermann. The theorem says that the conjecture is true for S2, and even more so. So it's a bit more precise. It says that if the simple spectrum of a Riemannian two-sphere is a singleton, then the sphere is simply Zoll. I didn't give the definition, but I'm going to give it now. So it's Zoll, and every closed geodesic closes up in a simple way without self-intersections. So I'm going to quickly sketch the proof of this theorem. It's the only proof that I will be able to sketch, probably. But it gives I won't give the complete proof, but at least I want to give the flavor of it. It's, not surprisingly, a variational proof. I'm dealing with simple closed geodesics, so I have to work with a space of loops which are simple. So let me denote by lambda. Lambda is usually reserved for the loop space of a manifold, but for me, lambda will be the space of unparametrized loops in S2.
The result is only from the many methods.
Yeah, so thank you. So I come back later to that point. Let's say that this proof is only valid for Riemannian, and provided one has a curve shortening flow, which is not available yet for Finsler. It should also be available. It should also, the proof will also go through for reversible Finsler manifolds. For other Finsler manifolds, there's point 2, and there's project number 2. I'll get back to it in a second, in maybe 15 minutes. So lambda is the space of embedded loops in my sphere, and I want the loops to be, I want really a point of lambda to be a one-dimensional embedded circle. So this is the embeddings of S1 and S2. Say smooth embeddings equipped with the infinity topology. And I don't want to keep track of the parametrization, so I actually quotient by the diffeomorphism group of S1. here's a crucial point. I quotient by the full diffeomorphism group, including the diffeomorphisms that reverse the orientation. That's what makes this proof fail for Finsler. I'll get back later on this. But the topology works fine for reversible Finsler. Yeah, so this is the space I will be working on. And actually, let me enlarge it a little bit. I denote by lambda star, lambda, this joint union with what I call lambda 0, which are the constant loops, the points. So this is essentially S2. And the topology is really, the topology is the quotient infinity topology, but it's the one you expect. Namely, if you take a sequence of loops that shrink to a little point, at the limit you get a point in here, in S2. So there's nothing subtle. And now the loop spaces have, the topology of loop spaces is rich. People have been studying it a lot. But this is not the usual loop space. This is the space of simple loops. It's actually much simpler. And I can describe the topology completely, very quickly actually. Let's see, maybe I continue the second backward. So here's your sphere. And so I'm going to denote by, let's see, I'm going to denote by G a space of great circles. So great circles are equators, possibly tilted. So for instance, this. So they're exactly the closed geodesics for the round metric. And a little bit of terminology, I'm going to call circle something that's parallel to a great circle. So for instance, this. So this is a great circle, and this is just a circle. So the space of great circle is a subspace of the space of circles. And both are contained in lambda star. And with a bit of abuse of terminology, I'm going to still call a circle the extremal point, which is just the limit point. So this is still a circle. So this point here is a circle, and it belongs to the boundary of C.
What do you mean precisely with the section of a plane?
So yeah, circle is the intersection of an affine plane with a sphere, and I allow the intersection to be tangential. So I allow the extreme case. It's an abuse of terminology. This say constant circle. But the boundary of this space, which is a closed space, is precisely the space of circles. So the boundary of C is precisely lambda 0. And now it turns out that at least the homology of my loop space relative to the constants is completely described by these two subspaces, namely, so it's essential here to work with Z2 coefficients, because somehow nothing is oriented. Then the homology of lambda star relative to lambda 0 is the same by the inclusion map as the homology of the space of circle relative to its boundary. And now, but the space of circle is, so the space of great circle is an RP2. So remember that these are non-oriented great circles. So every great circle is uniquely identified by the axis, which is an element on RP2. And the space of circle is the canonical bundle over RP2, tautological bundle over RP2. So this homology group is very well known, but by Thom's theorem, it's H star minus 1 of G, which is an RP2. So RP2 has homology in degree 0, 1, and 2. And therefore, this will have homology. So this will be generated by 3 homology classes, H1, H2 and H3. So Hi is the generator of the homology in degree I. And even more so, we have that the first cohomology group of lambda star is the same as the first cohomology group of the space C, which is the same as this first cohomology group of the space of great circles, and that's Z2, so it's generated by one cohomology class, which I'm going to denote by kappa. And last bit of topology, which is still very, very classical, is that these three classes are related. So Hi is equal to Hi plus 1 capped by kappa. And in case you're not familiar with the cap product, which is a basic algebraic topology operation, but all you have to retain is that if you have a cycle that represents Hi plus 1, compact subspace of that cycle will represent Hi. That's all you need for this proof, more or less. Okay, this is a topology, so very, very simple. And now comes the variation theory, which is due to Lustegnik and Schniegermann, but it's been a little controversial. So it's a solid variation theory since the 1980s, thanks to the work of Grayson on the curve shortening flow. So let's see, up to now I was looking at the sphere as if it were the round sphere, but now let's consider the given Riemannian metric. So I have my S2 equipped with my given Riemannian metric G, and I have an associated length functional. So L of gamma is the G length of gamma. It's well defined. So the length is well defined for unparametrized curves. So it's and this is actually not such an ugly space. It's the interior lambda without the star is actually a Fréchet manifold. You can even talk about regularity of this function and say critical points. This is not a smooth function, but you can still talk about its critical points, and the critical points are well known to be closed geodesics. So what you can do, since the domain of this function is topology, you can use the topology to generate critical points, so closed geodesics. And that was the idea of Lustegnik and Schniegermann. So you define Ci for I that goes from 1 to 3. So I equal 1 to 3. You find Ci to be the nth over all the cycles, say sigma, that represents the homology class Hi. Now the cycle is a compact subset of my domain lambda star, so I can take the max of L restricted to the cycle. Now this is expected to be a critical value, but as I said, it was a very controversial result for many years because the original proof of Lustegnik and Schniegermann was wrong. Nowadays we know that this is a critical value of the length. So this is really the length of a simple closed geodesic, thanks to the work of Grayson. Basically, the problem is that you don't have a gradient flow here. You don't have a usual gradient flow in lambda star, but there's a curve shortening flow, which is somehow the L2 gradient flow of this function. It has fantastic properties, and in particular, it allows to carry over all the classical arguments from critical point theory. So this is actually easy to see that it's positive, and once it's positive, thanks to Grayson, this is the length of a simple closed geodesic. Simply closed geodesic. Okay, so then out of the definition, thanks to these relations here, we see right away that these values are ordered like this. This is because, once again, once you have a representative for the class H3 that you use for C3, a subset of it will give you a representative for the homology class of C2, and therefore, if you look at it, you have the right inequality. And now, here comes the insight of Lustegnik and Schniegermann, which is a really, really important result. that says that if you have a quality, let's say if C1 is equal to C3, then, well, usually people state this result by saying if C1 is equal to C3, there are infinitely many closed geodesics with this length. But actually, Bursztyn and Stigman proved more. They proved that if this happens, then you consider the cohomology class kappa that you use to pass from hi plus 1 to hi. And so you take kappa squared. So kappa squared is what you use to pass from H3 to H1. Then it turns out the kappa square restricted to U is non-zero in the cohomology of U for every U in lambda, which is an open neighborhood of the set of closed geodesics, of simple closed geodesics with length C1, with this length. Okay, so this was the work of Bursztyn and Stigman, and now the theorem builds up on this, and it goes as follows. Let's see. I'll try to finish the sketch. I'm not sure I'll be able to. Let's see. So how to prove the theorem using this? Let's prove it. Let's say that, assume that G is not Zoll. Well, if G is not Zoll, it means that, here's your sphere. It means that there's a point on the sphere and a vector, tangent vector, V. So that's a point X. This is your sphere S2. So there's a point and a vector such that if you shoot the geodesic with this tangent vector, so if G is not Zoll, there exists a tangent vector V in TS2 such that the geodesic gamma V, which is once again the geodesic that you get if you shoot with the geodesic flow with this initial condition, is not simply closed. I put it in brackets, simply closed of period, of period, of length C1. So I put it in brackets to say that this is not true. Namely, this geodesic may be simply closed, but then it doesn't have length C1. Right, simply Zoll. Yes, everything is simply Zoll in this proof. Thank you. Yes, thanks. Okay, but then you can do the following thing. You take U, which is the set of all gammas in lambda, such that V is not tangent to gamma. So V does not belong to the tangent space of gamma. And now this, by this condition, U is a neighborhood of the set of closed geodesics with length, simple closed geodesics with length C1. Okay, but then I just borrow this little square. But then by Bursztyn and Stigman, but then if U is not, if U is a neighborhood, right, so now what you prove is that with a bit of algebraic topology, but these are not going, I'm not going over the details, but with a bit of algebraic topology, you can show that if an open set misses a tangent vector, then kappa squared must be 0 on this open set in H2 of U. But this implies that C1 is less than C3 by Bursztyn and Stigman, and therefore yeah, and therefore there are at least 2 different lengths for the closed geodesics. Okay, so I understand this is not a proof, but I just wanted to give the flavor of it. I don't know if you have any question about it. Okay, so where does the proof fail for Finsler? Everywhere, because if you have a reversible Finsler metric, you see that all the topological argument goes through again. The only problem is that you don't know that the min-max values are lengths of simple closed geodesics because you don't have Grayson's curve shortening flow. But curve shortening flow should be available for reversible Finsler. So let's say the proof is expected to go through for reversible Finsler, but it fails miserably for no reversible Finsler because the length function is not defined on this space if the Finsler metric is not reversible. Because when you reverse the orientation of a loop, its length changes. Nevertheless, the theorem is still true for Finsler, and actually even more is true, and this is what was quite surprising for me and also a little bit frustrating because it's something that I will prove in a second with symplectic techniques, whereas in I always had the naive idea that everything one can prove for closed geodesic can be provable without symplectic techniques, just with classical variational theory. So this is a counterexample. So it's good news for symplectic geometers. Yes, but this was already known. It was already known since pretty much since Poincaré, because once you know that you always have one simply closed geodesic, which you know it was a theorem of Poincaré that was made precise by Bombieri and Berger. Then if you have a Zoll metric, at least one of the geodesic is simply closed, but then all of them must be simply closed, if you think about it, because you have deformations. Right? But yes, if you want, the statement implies it. Again, I think it's not for simply connected Zoll manifolds of higher dimension. There's not one example of a Zoll metric that's not simply Zoll. But it's a bit strange because in higher dimension, simply Zoll and Zoll are kind of the same thing, because being simply closed is the same as being closed, because with the perturbation you kill self-intersections. So it's okay. So this was the first project, the beginning of the story for me, and now I'm gonna move to the contact setting. So I'm gonna talk about Besse and Zoll Reeb flows. So the first, so let me first give the definitions. I have to define Besse. Zoll Reeb flows, you can imagine what it is, but Besse I haven't defined it yet. So let me go over the definitions once again. So you have, say, a contact manifold, Y, of dimension 2n minus 1, any dimension. So this is closed. It's also connected. Everything is connected for me. I always forget that. If you don't put connected, most of the theorems are wrong. But, close connected contact manifold. And already defined in this conference the Reeb flow many times. So I'm going to denote by R the Reeb vector field. So R alpha maybe, the Reeb vector field of this contact manifold. And by, say, phi alpha t, the Reeb flow. So this is the Reeb flow. So the geodesic flow is a special case. It's the case when Y is the unit tangent bundle and alpha is the sometimes called Hilbert or Liouville contact form. And I can give the same definitions as before. The spectrum, the action spectrum of my contact manifold is a set of periods of closed Reeb orbits. Closed Reeb orbits. So closed orbits of this flow. And inside here, I have the prime spectrum, sigma p, of Y alpha, which is the set of minimal periods. Closed Reeb orbits. And now the definitions. So definition, alpha is Besse. So Besse, in case you never heard of it, it's like Bourbaki. It's the name of a collective of French mathematicians, I believe directed by Berger. And they wrote a very influential book, Manifolds, all of whose geodesics are closed. Well, they also wrote other books, Einstein manifolds, but they worked a lot on in this business for geodesic flows. So alpha is Besse when every Reeb orbit, so every orbit of this flow is closed. And so it's closed, but it may happen at different points in your contact manifold. The associated orbits close up after different times. Nevertheless, there's a classical theorem of Watzley. So I put it in brackets maybe. Watzley. It's a theorem about geodesic foliations actually, but it applies to Reeb flows because Reeb flows are geodesable. So the Reeb orbits are always geodesics for some Riemannian metric on Y that you can write down explicitly. Watzley theorem says that if alpha is Besse, then there's a common period for all the Reeb orbits. In other words, there exists positive tau such that the Reeb flow is the identity at time tau. So every orbit closes up in time tau. And now you can guess the definition of Zoll. Say a form alpha is Zoll if it's Besse and also every orbit has the same minimal period. So it's Zoll. Sometimes it's also called Butby-Wang in contact geometry. It's Zoll when, let's say, when for some tau, phi tau alpha is the identity, and in times less than tau, there are no fixed points for the time t map. So let's see, fixed points of phi alpha t is empty for all t between 0 and tau in the open interval 0 tau. So every orbit closes up precisely after period tau for some tau. Tau is the common period. Okay, so right. So the theorem I have with Dan Christopher Gardner. So Dan is an expert of three-dimensional contact geometry and is an expert also of embedded contact homology. So the theorem is in dimension 3 for three-dimensional. So Y is three-dimensional. And so Christopher Gardner and Hutchings proved a beautiful theorem that says that that extended the Weinstein conjecture of taubes in dimension 3. It said that every three-dimensional contact manifold has at least 2 closed Reeb orbits. And yeah, they even went further and proved that generically there are other 2 or infinitely many closed Reeb orbits. But it turns out that pushing a little bit more their techniques, one could prove a quite strong generalization of the theorem I gave before for for two spheres, which for Riemannian geometry is very frustrating, but we were very happy to be able to prove it. So theorem to Christopher Gardiner, and myself. I'm going to include Watzley theorem in the statement. So the statement sounds as follows. On a three manifold, the following are equivalent. Following conditions are equivalent. Condition 1, y alpha is Besse. So again, dimension 3. Y alpha is Besse. Condition 2 is what 1 implies 2, it's a Watzley theorem. Phi alpha tau is the identity for some tau. In condition 3, from 2 to 3, it's a very simple exercise. It just uses the fact that the red vector field is nowhere vanishing. The rank of the action spectrum is equal to 1. So in other words, up to multiplying alpha by a positive constant, all the closed web orbits have integer period. So let me maybe write it. So this means, or in general say, the spectrum is contained in the set of multiples of some positive number, say capital T, Z. So this is a set of multiples of T for some T. T is not tau, it's a different number. So the theorem is, the content of the theorem is 3 implies 1. Okay, but I state it this way because I like to say that this characterizes Besse content manifold purely out of the spectrum. In particular, the prime spectrum is a singleton. If and only if alpha is Zoll, which generalizes the theorem I had before, except that before I could also say that the geodesics were simple. That's a feature of geodesic flows. So this is a statement, and the proof is quite different. The technicalities of the proof are quite different from the proof I gave before for the geodesic flows. But conceptually, it's not so different. And no, sorry, I take it back. Conceptually, it's very different. And it also uses, it's based on a theorem that says that if two spectral invariants obtained with ECH embedded contact homology coincide, then the manifold is Besse. And by using this together with a very nice, beautiful asymptotic formula of Vinicius, Christopher Gardiner, and Hutchings, one can actually infer the result. Only have 15 minutes. I prefer to talk about the last. But I can talk about the proof maybe after the talk if somebody wants to hear technical details. It would take. Yes?
You don't need any first German class.
No. No assumption on the contact manifold. There's usually people that work with ECH, they like to assume that the contact form is Riemannian geometry would say bumpy, meaning that all the periodic orbits are non-degenerate, including all the iterates. And but we have a way to go around that in our proof. Yeah. No, it's no. Since I said there's no assumption on the contact form. No assumption on the contact structure and on. More questions? Okay, so what's the plan now? Let's see, I have 15 minutes. So let me first talk about higher dimension, which is project number 3 with Victor Ginsberg and Bajak Gorel. So in higher dimension, so up to now, a theorem like this for general closed contact manifolds is out of reach. At least, let's say statements like this are provable in a setting in which at least you're able to find one closed Reeb orbit. Otherwise, you don't even know where to start. However, in higher dimensional contact manifolds, at least for spheres embedded in the symplectic Euclidean space, something can be said. Not something this strong, but at least a spectral characterization of some kind of Besse contact forms can be said, and that's what I'm going to state now. So let's say this is chapter 3, maybe, high dimensional contact manifolds. And the first class I want to consider is the class that's the closest to the class of geodesic flows. So I'm going to consider the class of convex spheres. Say this one, for instance, sigma. Convex spheres in R2n. So R2n is equipped with a Liouville form that restricts to a contact form on sigma. So it's 1/2 x dy minus y dx, restricted to sigma. So this is a contact form. And I'm going to consider the Reeb flow of sigma alpha. And so this is a very special, so sigma, sorry, I didn't write it. So sigma is assumed to be, sigma is convex. Sigma is convex, this is always a contact form. And this is a very special class of contact manifolds. It's been investigated by Weinstein and most notably by Ekman and Hofer. And here I'm going to use so-called Ekman and Hofer spectral invariance. Spectral invariance. So Ekman and Hofer in the 1980s showed that you can associate to sigma a sequence of values of its action spectrum. They're usually denoted by C0 sigma, C1 sigma, and so on and so forth. They're ordered and then they diverge. And unlike in dimension 3 with ECH, the asymptotics of these values is something still mysterious somehow. Or at least there are still things that are not completely understood. And so these are all elements. So CI, every CI is an element of the spectrum of sigma. So they're all periods of the closed Reeb orbits. This doesn't mean that there are infinitely many closed Reeb orbits because the fact that you have such action selectors implies that there is one closed Reeb orbit, the one, for instance, carried by the one with period C0, but then you may have only that one, and C1 could be twice C0, and so on and so forth. They could all be multiples of the same period. Okay, and so these are defined by means of the Clark dual action functional associated to sigma, which I don't want to introduce, but for symplectic geometers, this is also related to the Ekman-Hofer capacity of the filling. There's no written proof of it, but these spectral values are expected to be a, so let me write Ci of sigma is equal to Ci of B, where Ci of B is the ith Ekman-Hofer capacity, which are, I believe, the Ekman-Hofer capacities are, I believe, the first examples of capacities that were built. So people usually know the first Ekman-Hofer capacity, which is in the convex setting, is the same as the systole. So this is known to be the systole of sigma alpha. The systole, this is a Riemannian terminology, the systole is the is the minimal period among all the Reeb orbits. So for geodesic flow, it would be the shortest length of a geodesic, of a closed geodesic. Okay, the theorem we have, so we have two theorems. The first one for convex, and the second one will go beyond convex. But the more satisfactory one is for convex, say. Theorem Ginsburg, Grau, and myself. So the first statement is a spectral characterization of Besse contact forms. It says that so sigma alpha is convex. R2n convex. So it's a convex sphere. First statement says that you have one of these capacities, say Ci of sigma, is equal to Ci plus n minus 1 of sigma. So n is the half dimension of the symplectic R2n. So this happens for some I. If and only if, and both directions are non-trivial, alpha is Besse. And the second statement that we have is, it says that this holds for the minimal I, so for I equals 0, if and only if, but it's a corollary of this, if and only if alpha is Zoll. So C0 of sigma is equal to Cn minus 1 of sigma, if and only if alpha is Zoll. This is a corollary of the first because I didn't write the full statement on the first. So we put comma, and in this case, Ci of sigma is a common period. Okay, so, oops, this is not me. Can I keep going? Do you still see the? Yeah. Okay, so I keep going. Huh? So the first theorem says these two coincides for some I if and only if we are in a Besse contact. We have a Besse contact form, and in this case, Ci is the common period for the closed Reeb orbits. Now, if this holds for I equals 0, then C0 is the common period for all the closed Reeb orbits, but C0 is the minimal period. So we have a Zoll contact form. So point 2 is a corollary of point 1. We also have point 3, which is actually a nice statement because it doesn't involve any technology, it doesn't involve any capacity or spectral values. It works for pinched spheres. So if you take delta, which is a number between 1 and square root of 2, and you assume that sigma, and you assume that sigma is delta pinched. So delta pinched means that here's your sigma. So inside sigma you can stick, you can squeeze sigma between say a smaller round ball of radius r and a larger round ball of radius capital R. And then you have that capital R mod R is strictly less than delta. Now actually, square root of 2 pinched spheres are a very special class of convex contact sphere. Many things are known for them. For instance, it's known that they always carry n periodic orbits, something that is an open problem for general convex spheres. So here the statement we have is the following. So then it turns out that if you want to know whether a pinched sphere is Zoll, it's enough to look at this action spectrum near the systole. Namely, sigma is Zoll if and only if you take your action spectrum and you intersect it with the open interval between the systole of sigma and delta squared, the systole. And so sigma alpha is Zoll if and only if this intersection is empty. Okay, I think the most interesting case is the limit case when delta is square root of 2. You have a square root of 2 pinched sphere. You look at the periods of the closed web orbits. If there's no period between the shortest possible period and twice the shortest possible period, that happens if and only if alpha is Zoll. And right, so and finally I have 3 more minutes, so let's see if I can state the last theorem. Now, if we drop the convexity, things are a bit more complicated. And actually, we didn't manage to prove a result in this generality. So we have something slightly weaker, but it's still a significant statement, in my opinion. So assume now that sigma is just a contact sphere in R2n. So sigma alpha is contact. It's a contact sphere. So it's not convex anymore. It's in general star-shaped. So here's a sphere, sigma. So it's star-shaped. It encloses the origin with respect to the origin. So that alpha is the one form that I wrote down before. So the theorem we have here it's only one direction of point 1. So here we don't have Ekelhofer spectral invariant. We only have the Ekelhofer capacities. And the theorem requires an extra assumption that the action spectrum is discrete, which is the case for Besse contact forms thanks to Lee Theorem, but it's a bit of an annoying assumption that we hope to remove. Maybe not so easy. But, so if the action spectrum is discrete and the Ekelhofer capacity I of the filling, so I call B the filling, the compact filling, is the same as so if this is discrete and the ith Ekelhofer capacity of B is the same as the ith plus n minus 1 Ekelhofer capacity of B, yeah, then sigma alpha is Besse, and this is a common period, and Ci of B is a common period. So once again, this assumption I don't think it's essential, but things get a bit complicated if we don't require discreteness of the action spectrum. So what we don't know, maybe I write this as a question, but I'm not sure it's a question. I think I would expect it, but question or conjecture. What we don't know is the opposite, actually. That if sigma is Besse, do we have Ci of B equal to Ci plus n minus 1 of B for some I? And my feeling is that the answer is yes. If sigma is Besse, the idea is that you take the common period for the closed web orbits, you look at the Colli-Center index of the orbits at that period, and that Colli-Center index should be twice I plus n, and I is the one that satisfies this. But that requires proving that Besse implies that some action function is perfect. It's a work in progress. But, over time, sorry, stop here. Then